Today, we're going to learn about quantum numbers. There are 4 different numbers, called quantum numbers, that are used to describe the location of the electron within the atom. Before we talk about them, remember Heisenberg's uncertainty principle. This principle states that it is impossible to know both the exact position and the exact speed of an electron at a given time. Because of this, we use quantum numbers to describe the most likely location of an electron in the atom. The first quantum number is the principal quantum number, represented by n. The principal quantum number describes the main energy level, also called the shell, where the electron is found. It tells us the size and energy of the atomic orbital. The possible values of n are positive whole numbers, 1, 2, 3, 4, and so on. As the value of n increases, the electron is farther from the nucleus and has more energy. This also means that electrons with higher energy are less tightly bound to the nucleus. Think of the principal quantum number like the floor of the apartment building. The higher the floor number, the farther away from the ground you are, or the nucleus of an atom in this case. Now, the second quantum number is the secondary quantum number, which describes the shape of the electron's orbital and is represented by the letter L. The values of L range from 0 to n-1 for each energy level. For example, if n equals 1, then L can only be 0. If n equals 4, then L can be 0, 1, 2, or 3. Each value of L corresponds to a different orbital shape. If L equals 0, the orbital is an s orbital, which is a sphere. If L equals 1, the orbital is a p orbital, which has a dumbbell shape. If L equals 2, the orbital is a d orbital, which has a cloverleaf shape. If L equals 3, the orbital is an f orbital, which has a more complex shape. Think of the secondary quantum number as the type of room in the apartment, like 1 bedroom, 2 bedrooms, and so on. The third quantum number is the magnetic quantum number, represented by ml. The magnetic quantum number describes the orientation of an orbital in 3-dimensional space. The values of ml range from -L to +L, including 0. For example, if L equals 1, then the values of ml are -1, 0, and +1. If L equals 3, then the values are -3, -2, -1, 0, +1, +2, and +3. Each value represents a different orientation of the orbital. Think of the magnetic quantum number as the direction in which the apartment faces, like north, east, west, etc. Even if apartments are the same type of room, they might be oriented differently in the building. The fourth and final quantum number is the spin quantum number, represented by ms. This quantum number describes the spin of an individual electron. Electrons can spin in one of 2 opposite directions. Therefore, the only possible values of ms are +1/2 and -1/2. In any practice problem, ms is always +1/2 and -1/2. Think of this as whether the apartment is occupied by a person who is right-handed or left-handed. It represents the inherent property of the electron, describing its spin in one of 2 possible directions. You can have only 2 possible values, upspin or downspin, much like a person can be either right-handed or left-handed. Now let's talk about an important rule called the Pauli exclusion principle. The Pauli exclusion principle states that no 2 electrons in the same atom can have the exact same set of 4 quantum numbers. In other words, every electron must have a unique combination of n, l, ml, and ms. 2 electrons can occupy the same orbital, meaning they have the same values of n, l, and ml. but they must have opposite spins. That means if one electron has a spin of +1/2, the other must have a spin of -1/2. Now, let's practice. Suppose you're given the principal quantum number, n equals 4. First, let's determine the possible values of L. Since L ranges from 0 to n-1, the possible values are 0, 1, 2, and 3. Now match each L value to its orbital type. L equals 0 corresponds to an s orbital. L equals 1 corresponds to a p orbital. L equals 2, it corresponds to a d orbital. L equals 3 corresponds to an f orbital. Since n equals 4, place the number 4 in front of each orbital letter. That gives Another question can be list all the possible quantum numbers for an electron in the 5f orbital. 5 represents the principal quantum number, or the energy of the orbital. Therefore, n would equal 5. Next, L would not equal 4, because you are already told that there is an f shape, which is equal to 3. So L equals 3. Next, ML is always the range of L, so it would be -3, -2, -1, 0, 1, 2, 3. And MS is always +1, half, -1/2. Together, these 4 quantum numbers uniquely describe every electron in an atom. Thank you for watching. Like and subscribe. Comment down below what other lessons or concepts I should go over.